Okay, so we will start a new project with the dynamic analysis itself. So for that, actually, if you just go, so I hope you guys all are doing this. A dynamic analysis on a generator of an elastic foundation. This is what actually we will do this. So for this, actually, the sufficient documents that I have already enclosed it here. And if you see that there is a one log file and one PDF file. This is the log file. So if you just download that particular attachment, we can able to see the complete code too as well. Okay, I'm just simply copying this particular thing and then going back here. If you're going to the small scale industries, you might not have this particular option because they won't come under the annual maintenance all the time. To save the cost, actually, they won't come into the annual maintenance so that you won't see that particular option. Yeah, fine. So we are going to learn some new options today. So please be very careful on understanding these options. And if you have any issues also, please stop me there itself and then we get rectified over there, because the dynamics is one of the complex topic, but if you understand that, that is the easiest one when compared with any other things actually. Okay, now moving on, the dynamic slides that we have seen it already over here, and we will just getting into this consolidation safety. So we have seen up these particular things and all. So now when we see these particular things, this is the input values that we have seen, but one more thing that we need to understand, it is called as a dynamic analysis boundary conditions actually. So when there is a geometry, like you have built the soil layer and you are applying some load, and because of this load, actually the vibrations are coming and then hitting up to your borders over here. Okay. So when these waves are coming, I mean, you can't see with the naked eye, but when you put some vibrators or the sensors, it will able to measure with what frequency it is getting vibration, and then we will come to know about these things. Okay, when it is coming it over here, a vibration will have a high amount of energy, and with that amount of energy, when it is hitting this, as we don't have any other supporting soil over there, so when it is hitting this particular object, there is a unnecessary deformation will happen. So that means a force coming here, and because of that, the soil start moving over there. And the moment when it reaches to here, if it is hitting with a higher force, a high amount of a force, then unnecessary deformation will happen or unnecessary stresses will create at the borders. But it is not our requirement. In reality, if you say that if you place an impact load, suddenly you are dropping your foundation onto your excavation part. Okay, now the vibrations will come, but when you see in the real world, the site area surrounded to that particular foundation is infinite. You want to see a vibration level up to like 2 kilometers, 5 kilometers, 10 kilometers, 100 kilometers, anything is possible. Okay, when these particular vibrations are getting completely nullified, is that we need to understand that. So it's very difficult for us to get nullify that at which particular point it is going and stopping over there. But just to avoid some type of a complexity issues, that's where wherever the region that we were applying, suppose if this region is like 5 meters, then we were going like 5 times, as you have seen in the axisymmetric model for the first time. The same thing there, actually it's like 3 to 5 times I told. If it's a static analysis, that is the plastic calculations, you go with the 3 times. But if it is a dynamic analysis, it is must and should that you have to go for the 5 times. Okay, yeah, after going with 5 times also, still you see that there are vibrations coming and hitting these particular boundaries. Okay, now I need to nullify this one. That means I need to send a cancellational signal to this, saying that, oh, vibration is coming and hitting this particular border. Just observe whatever the energy it is coming, and it should not reflect it over there. Okay, you have to observe the complete energy. So for that, actually, we are deriving or we are achieving that with the boundary conditions. Normally in a plastic calculations, what you're doing, you're going with the fixities, right? As I have showed somewhere actually. Yeah. You see this one, the boundary conditions for a static analysis are like a you're going for these particular deformations, and you can see these are the fixities that we were using it. So this condition is a normally fixed, and this is a fully fixed, and this is a fully free. We were living like this. So similar to that, even the dynamic analysis also that you have to follow. So the dynamic analysis to follow that particular part, these are the boundary conditions that we have it at the same region itself. Like if you just go for the Plaxis, when you just go for the Plaxis, in the stage construction module, if you just go and expand your attribute, there you have like this called as a dynamic filters. This is how you are creating your dynamic values and all. Okay, this is how actually you're creating a dynamic values. After creating these particular things, that you have to go for your model conditions. In the model conditions, that you have to go for a dynamics. Previously, that what we are going, we were just going for the deformations, and then these are the boundary conditions that we were checking it. Okay, that's true. We need the deformations boundary conditions, and along with that, we need the dynamics boundary condition also to be switch off. The moment actually, when I select this particular footing, now you can see these things. Here also the dynamics is added. And when I select for the initial phase, here also the dynamics is added. Okay. For example, not this one. I'm not saving this. I will just simply do one small thing over here. That's where you add a one particular soil layer. That the soil layer is having some 50 and the groundwater is there. And the materials, if you would like to go, you can just copy some sign here and you can assign the same sign. Just give OK. If you just go for the file, project properties, here in the model, you'll just come to know the X maximum that I would like to maintain as a 50 mm, or like you can just go it as like a 150 mm. That's why this is increased. Okay. Now going to the structures, actually what I do, I was creating some load. Let's say a line load I'm creating it. So from this particular point to this particular point, you are creating a line load. Now, after creating this particular line load, I would like to say that if I select this particular line load, I can expand in my selection explorer. In my selection explorer, I can expand this one. And then here you can see there is an option called along with the line load previously that you are going. And here actually what you are giving this in the y directions, it is like a 1 kilonewton per meter. By default, it is applying it. In x direction, there is nothing. But if you'd like to apply the x direction, that is like a compound force, it will come. Like one, you can just say inclined force, it is going to be generated. And the compound force is like 1.414 kilonewtons. Okay, simply not complicating this one. I'm just going only for the vertical forces. Now in the y directions that I can see, it is like a -1. And now the saturated reference here, I can see that this is a 1 kilonewton per meter square. Okay, fine. To this, actually, I can able to apply the dynamics part. When I just go for the dynamics part, it is asking that distribution is a uniform or it is a linear function, perpendicular or a perpendicular and vertical functions actually. Suppose if you select this as a uniform, then you have to select this actually. What is your value? What is your value actually? Okay. Uniform directions that you are applying it. You are applying in which direction? This is a y direction. In the negative y direction, I'm applying it. So by default, if you don't know anything also, keep it, you know that it has to be applied in the negative direction. That's a compressive force that you are applying it. It is not a uplift force, it's a compressive force. So that it's like a -1 in the -1 directions that I would like to apply this. Okay, make sure that here actually you are applying only the line load. If you didn't apply this line load also, that's fine. That's -1 is nothing actually. It's anything multiplied with 1 is only that. 1 into 1 is 1. 0 into 1 is 0, or like 100 into 1 is also 100. So it's not going to change that particular factor. So 1 is a good value, no issues. Okay, now I have set up this one. After setting up this particular thing, now I need to tell to the thing, either this one, whatever I have created just now, is it a linear one, like it's a harmonic response, or it is a something like a tabulated response that I need to feed this. To feed that particular values, what I can do, I can just go to the attribute library, to the dynamic multipliers, right click on this dynamic multipliers, click on this edit button, add this displacement multiplier, and name the displacement multiplier as a test one. And the signal is like a harmonic signal, and the amplitude I'm giving it as like a 5. So amplitude is like a 5, and I'm feeding that as a displacements, and it is now obviously it's not a 5 meters, so it should be like around some 0.2 meters, and the phase angle is 0, and at a frequency of a 10 hertz, you can say that. At a frequency of a 10 hertz, you can say that. So to form a one particular cycle, it is taking you around like exactly 0.1 seconds. Okay. So now just give OK for this one. Now you have these particular dynamic multipliers as a test one. After creating this model attributor, you have to go to this particular dynamic load, and in the multiplier, you are applying this multiplier in a y direction. So you just select this multiplier y. Okay, I have applied the load, and here I have created the displacement. That is the reason it is not showing. Okay, fine. So you can just go to the multiplier y and the load displacement, load multiplier 1 with an amplitude of like point, or with an amplitude of like some 50 newtons of a load, kilonewton per meter that you are applying it, and with a frequency of around 10 hertz that you have applied over there. Now this is where it is going to come. So just give OK. So now if you see this one, the multiplier of a load multiplier, it has been created. Here what I created, this one is not required. This is a displacement multiplier. If you apply a displacement multiplier, then it will come. And now the load multiplier signal is a harmonic one. Amplitude is a 50, that is 50 kilonewton per meter that you are applying it. This 50 in the analysis, this 50 will be multiplied with this particular one. That is what I am trying to explain that in this particular slide actually. If you see this one, in the selection explorer, if I just go by expanding this particular, I have showed you a line displacement over there, right? Sorry, line load I have there, but in the slide I have just kept it for a line displacement so that we can cover both the things. Okay. So in the line displacement, if you see that one, so in which directions that you are applying, that you need to select this one, and how much you are applying, you selected this one. Now actually what will happen, you are feeding it as a tabulated values. Now to these particular tabulated values, this -5, that is in the negative 5 into 0.05, it will happen. What will happen? This is like 5 into 0.05, it will happen. That is 0.25 meters of a displacement will apply at a first stage. Next is like 0.09, it is coming, right? So that is nothing but around some 0.4 or 0.45 meters of a displacement it is applying. So the value that you are providing here, it is very, very important. This value will be multiplied with these particular values, and then you are going to get this one. So as a similar way here also, if you see this one, that's where I told you to keep it as a 1. So what will happen, majority of the times people forget to keep a 0 over, I mean, default it is going to come as a 0. Forget to keep a negative or the positive direction values like a unit value 1. They used to forget to keep that particular values. That is the reason the dynamic model will not apply on the model where you can able to see a wrong results. Actually, I'll show you that. I'll show you that too right now. Okay. So keep this as a line load that I was applying for this, and then I'm just going here, right? So now I'm just going for the mesh, generate the meshes actually. It's a simple dynamic analysis I'm doing it here. I've just undone the mesh. Flow conditions are similar to that, and to the stage constructions I'm going it. Now this is the first phase, initial phase, where I would like to activate my line load. So what is the line load that you are activating it? Maybe the unit line load only you are activating it. Suppose the very first phase itself you are activating the dynamics part 2 as well, then this should not be the plastic calculation. This should be a dynamic analysis. A, a dynamic analysis that you need to select it, and what is the time interval that you would like to run the solution. Okay, at a frequency, I know to complete a to and fro motion, it is taking 0.1 seconds. Like that, how many number of cycles that you need to run? Okay, so I need to run for 100 cycles. So 100 into 0.1 seconds, that's where like some 10 seconds or that you would like to solve this particular problem. But 10 seconds is like a very huge time in the dynamic analysis. Okay, I would like to solve it for 0.5 seconds or 0.05 seconds also people will use to do that. Okay, let's say that 0.5 seconds that I would like to do, but there are like days also you can able to go for this, but make sure that dynamic time interval, it is always in seconds. It is always in seconds. Okay, by default, it is always in seconds. Okay, 0.5 seconds I'm trying to run this. Other things, whatever it is there, everything is default I'm leaving. Just give okay. After giving that thing, so now what you need to do, you have to go here, activate this particular dynamic loading also, where you already given these particular load values and all. And now you have to expand to your model conditions. Now in the model conditions, you see that the dynamics is activated. If you go for your initial phases, the dynamics is also activated. And if you go for the phase 1, the dynamics is also activated. And if you expand this, suppose if this problem is something like it's not the dynamics, it's just a plastic calculations that if you are considering this particular thing, then if you uncheck the dynamics also, that's fine. But by default, the dynamics is also in switch on mode. So follow the same thing that what you have is there actually. Okay, now, sorry, it's about the dynamic analysis. We are solving it for 0.5 seconds. Yeah, now the dynamics is on. Okay, and then go for this model conditions, dynamics. Now you can see this. The default, what is this particular boundary conditions is what I have discussed here. Now, if you see these things, these are the boundary conditions that we will see. X minimum, X maximum, Y minimum and Y maximum, all 4 directions that we can see that. X minimum, I'm saying, this is the X minimum direction. So X minimum, I'm telling that it's a viscous boundary conditions. What do you mean by viscous boundary conditions? Viscous boundary conditions are the conditions when these boundaries are hit by a huge amount of energy, then these particular boundaries will absorb that particular energy without any deformations. Okay, so that means when a high amount of a wave or a tide it is coming and hitting this particular boundary, because of that actually the deformation should happen at this particular places, but now that particular deformations will not happen. It will simply observe that particular conditions. It will simply observe that particular conditions. That's where actually the viscous boundary conditions, you can say that it will also observe the vibrations coming from the source. Okay, and now here if you see this X minimum as a viscous echo, and then X maximum as also as a viscous, they have kept it. And Y minimum, if you see this is the Y maximum direction, this is the Y minimum directions. So the Y minimum directions, they have not kept anything. And Y maximum directions also, they have not kept anything. And there are the other factors. Okay, now if you see, you can see only the viscous and none, but there are the other options as I mentioned in the PDF too, as I mean the presentation too as well. Here you can see that viscous, free feel, 5 degrees of freedom, you can see this. Okay, so now I just choose this as a viscous, right? So now if you see this thing, viscous is what that we have learned. Free field is completely, it is a free actually. So if a vibration is coming and hitting that particular boundary, because of that particular hitting, what is the deformations on that particular boundary, if you would like to study those kind of a thing, then you are free to choose this particular free field only. But there are one more option that's called as a tight degrees of a freedom. It's a user choice to define the constraints for the dynamics actually. So, okay, I want the deformation to be recorded C only in the X directions, but I don't want to see the deformations in the Y directions. Then you can able to see what is the tight degrees of freedom that you can able to see over here. Next is called as a compliant base. Compliant base. Okay, let me briefly explain you what is the tight degrees of freedom to as well. If you go over here, and in this particular image, if I see, because of the vibrations over here, a vibration it is coming and hitting my Y minimum, and after hitting this particular things, I would like to see, okay, the vibration can hit here, and after that it can reflect it back to as well. Because why it will reflect it back, it is not deforming this, because already I have a deformations here. So in the boundary X minimum, it is already normally fixed one. So there is no chance of a deformations at all. So that the vibration which is coming over here, it will hit and it will come back. Okay. If I wanted to simulate that kind of a nature, then you have to go with like a free field. Sorry, free field. Okay, we just go with like a free field. So the free field will go and hit that particular boundary, and then as the already a normal fixity it is there, so it will come back. If it is not like this, if you would like to go for a tight degrees of a freedom, okay, so now if you just go for this particular tight degrees of a freedom, then it will ask you like which directions that you would like to tide. Okay, in the X minimum direction, that is in this particular direction, X minimum, that is only this horizontal, not the vertical directions. Only the horizontal deformations to the minimum side I'm restricting. And if you see this one, X minimum and X maximum, it will not allow me. So this side I want to make it as a free, but the other side I would like to take the records. This is physically not acceptable. That's why when you see this one, when you click on this tight degrees of freedom, both the sides it will become a tight degrees of freedom. When you select this as a free field, both the things will become as a free field. And when you select this as a viscous, both the things will become as a viscous. So what you follow for X minimum, you have to follow the same for the X maximum too as well. Okay, but why I can't see the compliant base here? There is a one more thing, right? So which is a compliant base actually. So why I can't see the compliant base in the X direction? Compliant base is the one actually we will use this dynamic applied onto the base side. Example for the earthquake data. Earthquake will come from the bottom, not from the horizontal directions or not from the above. It will always come from the bottom surface. So that's why if you see this one, Y minimum will always have a compliant base. If you just go for this Y minimum, here you can see that there is a compliant base. But here you can't see the high degrees of a freedom or like a free or something like that. What will happen if I take it as a free? The vibrations coming over here, it will hit and it will completely going on. To which distance it will go, it also don't know it. Okay, so that's what it will happen it for this. So that's why, yeah, if you just go for the Y maximum also, you can't see that particular compliant base. So earthquake data that if you would like to feed, you can able to feed only from the bottom direction. So that's why the software is restricted for this. The X minimum only you can able to see the compliant base, but you can't see that in the, sorry, X Y minimum only you can see the compliant base. You can't see it in the Y maximum. So take a pause here and let me know that if you have any doubts or any difficulties in understanding the boundary conditions of a dynamic analysis and how we are feeding up the attributes here, how we are sorry, how we are feeding up the attributes here and how it is taking into the software. I'll take a pass. Let me know that if you have any doubts here.
No issue, bro.
I want from everyone because this is a complex topic, but once if you understand, this is the easiest topic. Okay, let me show you an example. Give me a second. Okay, now I've just selected this as a dynamics one. And now let's say that X minimum maximum is viscous and Y minimum is a completely, and Y maximum is a none, and the Y minimum is like again the compliant base, or like I can just go as a viscous. Okay, but if you see that in the Y minimum directions, oh sorry, yeah, the Y minimum directions, instead of the viscous, if I just choose it as a compliant base, then actually I can able to draw a line load over here, and then I can able to apply the load. That I'll slowly tell you that. For the time being, we just consider that is also as a viscous boundary. All are viscous boundary conditions, and this is none at the top actually. Okay. Now try to run a problem. Ignore the feedbacks that we didn't pick any notes for the calculation. That's it. Now, if you see this, guys, actually, whatever the sine curve that I have given as an input, the same sine curve it is going to generate it over there. It's going up and down for 0.5 seconds that I have solved it. Okay, but if you would like to solve it for 10 seconds, this is a simple problem that you can solve it for 10 seconds, but reality, you can't do that. Just for a better curve, actually, you can see that. And that's the reason I'm just plotting this. Mhm. Just stop me here. I would like to recalculate this one. Select this particular line load. Yeah, this is the reason actually. When I select this particular phase, the dynamic load and the line load also should be unactivated in this. So both are not activated. That's the reason why it is trying to solve this. It's simply running this. Okay, fine. Just line load also you can activate this thing. Mm-hmm. No, not as expected. 50 kilonewtons of a load to apply at 10 hours of the face angle of this one. Okay, for every 0.1 second actually it should go up and come down. 0.5 seconds, this is also good value. That hmm. Hmm. Hmm, hmm. Why again this is getting line loads? I need to activate it here. Under the line loads, if I just go for this is the line load. And in this actually the dynamic load also I'm activating here. Now calculate this. Okay, this is a displacement versus a time I'm looking for this. Okay, this is not the right way actually. The line load will not be the right way. Let me do one thing. Create this as a line displacement. And when we just go for the line loads, we can delete this particular line load. So this is the line displacement. Then if you see this one, X is a free and Y is a prescribed one, and then the dynamics one. So I would like to create not this particular load multiplier. I would like to create this a displacement multiplier with an amplitude of like 0.5 meters. You can say that is also huge at a frequency of 10 Hz. Then just give OK. Then go for the multiplier and you can just choose this one and mesh it. You can apply the load too as well, but just for the graph purpose, I'm coming back and creating the displacement. Now you can come to know the importance of it. Like for 10 seconds, the line displacements that we were activating here. And if you select this one, along with that, the dynamic displacements also that we need to activate. Yeah. Okay. So now let me solve this. A 0.5 meters, it's maybe the too huge. 0.01 I'll apply. Half a meter distance might be the very huge distance for the dynamic load. or for the particular soil. Let me do one thing. Still, it is not in the expected way as what I add this. Add this as a dynamic analysis and solving it for 5 seconds. Okay. Now the line displacement is activated and the line dynamic displacement is also activated. This 0.01 meters. 0.1 we try. 0.1 is also big one. 0.05 we can see. The frequency of a 10 hertz actually. So when I just go for this displacements here, if you start from 0, by the time when reaches to like a 0.04 seconds, one second. Okay, it's coming there, and then again it's coming down to like here. So by coming to 0.1 seconds, actually 1 cycle should complete. 0.1 second 1 cycle should complete it actually. It's a displacement only. It's a harmonic signal. Fine. Y is the prescribed one, uniform, and it's having like speed there. This line displacements I can activate it here. Okay, it's not in the negative direction. It's in uniform. And saturation will just keep it as a 1. Oh, sorry. It's like -1. Multipliers, displacement multipliers. I just provided this. Data type is also displacement. Dynamic multiplier, signal is harmonic, everything is good here. Why it is not performing in the way I expected? Line displacements. I need to activate the line displacements, and then I need to deformations, dynamics. Just go for the line displacements. solve this one. Everything looks to be good, but why? If it is not coming, then you have to close it and then reopen it again. As this is a 0.1 second, as the time reaches to a 0.1 second, it should go one up and down curve actually. But this, the displacement, it should go up and it should come down. No, this is not the way I expected to us. Where I did wrong, where I did wrong. Okay, let me do anything. I'm not saving anything here.
Hello.
Hello.
Uh, actually,
Sorry, there was a
what
power
is?
down actually.
Okay. I thought my screen froze.
No. Actually, there was a power shutdown, so it take time to start the Wi-Fi with the backup. Okay, fine. So this is where actually the line load only they have taken it here, and then let me solve this once. We'll just come to know what kind of a graph I'm expecting. Yeah, this kind of a graph actually I'm just expecting. So it has to go go up and down, go up and down. So this is how actually that I was expecting from this. Was someone waiting? Okay, fine. So as this is one thing, as the vibration is coming down, it is cooling over there. This is a very simple thing. So let me do one thing. This is also the line load that they have taken it, and then we can see that. Yeah. So what they have selected is like an attribute library. Dynamic multipliers, the load multiplier. If you just go and edit this load multiplier, they have taken amplitude and frequency as the values and the phase as a 0. So that's where like they can able to finish one cycle up, down to the middle. So in 0.1 seconds, they can able to finish this. That's a load multiplier only. And coming on to this, actually, if you see this thing, as a generator weight is a 8 kilonewtons of a load, and over that they were applying some thing, and the signal is a harmonic. So this way actually that we were good. So we were also having the same weight, and then we were doing this one. And coming on here to the model, to the geometry, if you see that, to the lines, okay, to the model conditions, and to the dynamics part actually, Y maximum and okay, X minimum is something none because they have taken up the boundary conditions over here. And to these things only they have taken up the boundary conditions. That's why they can able to see these things. Okay. Then why can't we see that? Well, let's go with some 100. Add this to in the negative directions like 10 meters. I'll bring up the sand. Okay. Now to the sand, the groundwater head water level, I can say it's like -5. And to the structures module, I can just go for the line load itself. The line load. And to the dynamic multipliers, we can choose this as a line load. We can choose this one. The 10 as a load, and then the multiplier frequency is also like a 10. Okay. And then actually what we can do, we can just go over here. This is the weight actually that I would like to apply. This might be some -5 or of value that we will give. Okay, let's consider that there is a weight of it, a component. And now this dynamic line load that we are applying it in the negative directions of -1. The load multiplier is this that we have selected these things. Go to the mesh, generate the mesh, stage constructions, add a phase. This particular phase is a dynamic analysis phase, and we were solving it for 5 seconds. Then we are activating this particular things. So when we just activate this, the dynamic load also need to be get activated. Okay, let's say that first you activated only. Okay, we can do this. So yeah, now the dynamic load is also got activated. See this one. That's the difference actually, the dynamic load activation and not activation. Previously that we can't see that actually. Fine. Now to the model conditions, if I just go here, this is a dynamics part and the viscous, and Y minimum is also like viscous we can keep, and then the Y maximum is none. Okay, fine. Good. And now we try to solve this. Now you see this, there is an up and down of these particular values that's going on. That depends upon the frequencies or how we were calculating the particular values. That's purely dependent on that. So that's how actually it is generating over there. Okay, that's the line load that we have given it. That's why you can see that particular frequencies. Let me do the same example with the line displacements too as well. And for the line load, it's crossing 1 second of a dynamic time. But here it is showing the displacement, not the ultimate U value. Perfect, 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 perfect. I was just trying to look for the whole solution, but don't do like that. My badness. I'm sorry for this. Just go and pick the point that where you are interested. I was applying the dynamics on this particular part. So pick at that particular point, how the dynamics it looks, that we can see that. Update. Now to this actually you just try to solve this one. Can you see that the curve now as what we expected in the same way? That's where I just missed only one particular point that I just forgot to pick the right point over there. Now this is how actually on that particular point, the complete up and down forces it is coming it over there. So due to the initial displacement and it is coming down, after few days actually the deformations it is reaching over there. And now you can see, previously you can see here it's a U max, but now you can see it's a delta. Now this is the one I was expecting here. Okay, only thing is like I've just picked up a point here. As a 548 is a node that I've picked up here. Okay, it will take time to solve it as it is at 5 seconds that we have done. And you can see this is the complete graph it goes on. Yeah, that's totally fine now. Like if you see this one, this is what I'm expecting to as well to this particular structure. Yeah. So with this, I would like to take a pause here, a break, and then we will continue further onto the same dynamic analysis tomorrow also. As I told you, like again on Friday, I'm going on a break, right? So tomorrow I will be taking you the class so that I can try to finish the dynamics part so that you can start practicing it. Dynamics may need a lot and a lot of time so that you'll get a plenty of time to as well to practice it. So you can start doing on that particular way. Maybe at the okay. Maybe at the starting that you may feel that it's too difficult to understand or something, but don't feel like that.